Ladies and gentlemen, class recording has started. So, on Tuesday, we introduced the concept of force. And we said that force does what? Pushes or pulls. But what happens when it pushes or pulls? It changes an object motion, right? It's acceleration. It causes acceleration. Okay? So, yesterday, we started talking about Newton's first law, an important concept dealing with force. And while Newton's first law has a big, long explanation, a big, long statement that summarizes things, we can basically use one word to represent the gist of Newton's first law. And what is that one word? Inertia, right? Inertia summarizes Newton's first law, in that inertia says that an object is going to do whatever it is currently doing, right? Object at rest remains at rest. Object in motion continues in motion with a constant velocity until it experiences a net external force. That's the gist of inertia, right? So then we turned our attention to the net external force part. When we talk about the net force acting on an object, what are we describing or what are we explaining? How much force is being put on an object, but we have to take into account not just one force, but the total amount of force, right? All of the forces. And we said that sometimes we can use either of these notations to represent net force, right? F with the subscript net, or we can use the sigma notation. We said the sigma mathematically represents the sum, or the whole, right? So, when we look at an object, we have to look at all of the forces that are acting on that object. So here's a picture of a tug-of-war. And the rope has two forces acting on it. The yellow team is pulling to the right, the blue team is pulling to the left. If the rope isn't moving, what has to be true about those two forces?
No, there's a zero net force.
There's a zero net force, so those two forces would have to have the same
energy. Gravity.
if the rope is not moving, so if the rope is not moving, hold on. If the rope is not moving, that means that the net force is zero. So that means, and then we said that the description of that is called equilibrium. Okay? But if we looked at these two forces compared to each other, they would have to have the same what? Magnitude, but different direction. And that's how we end up with a net force of zero. Okay? Good there? Now, we could have more than two forces. If we had like two forces in the blue direction and one force in the yellow, if blue was 5 and 5 and yellow was 10, we'd still have equilibrium, as long as the total adds up to 0. Does that make sense? We okay with those two? Okay. So, generally speaking, good. The magnitude is how hard we're actually pulling or pushing, right? Remember, magnitude is how big or how much. So when we're talking about force, it's how hard are we actually pushing or pulling. Or if we go back to Tuesday, how many newtons of force is there? But we can't just talk about how much force there is. We also have to talk about which direction that force is pulling. So if this is 10 newtons to the left and this is 10 newtons to the right, negative 10, positive 10, total is 0. But it would also be the same if we had two 5 Newton forces to the left and one 10 Newton force to the right. Because when we do the total, negative 5, positive 10, that gives us 0 too. Okay? All right. Good with those ideas. So, Newton's first law deals with inertia. And inertia is an object staying the same. So if Newton's first law deals with things staying the same, what do you think Newton's second law deals with? Things that are changing. All right? Jafar, what one word talks about things changing? What word describes the change in an object? Well, delta is generally speaking the change, right? But when we talk about the change in the motion, acceleration. So Newton's first law deals with inertia. Newton's second law deals with acceleration. And Newton's second law says that the acceleration of an object is affected by two things. One is the net force that is acting on that object, and two, the mass of that object. We summarize how the net force and the mass affect the acceleration with these equations. F net is equal to m times a. Or we can just rearrange that equation, get a by itself, and do F net, or a is equal to F net over n. So the acceleration of an object, how much it changes, depends on the net force and the mass. This equation right here, F equals ma, it might not be the most famous equation in science. That's probably E equals mc squared. But you deal with this one a lot more than you deal with E equals mc squared, right? So this idea and inertia are basically going to be your life for the next week and a half. Okay? All right, so let's talk about this equation. F net equals ma, or this one especially, a is equal to F net over m. If we increase the force that we are applying to an object, but the mass of that object stays the same, right? This is a fraction. If we make the top of the fraction bigger, but keep the bottom the same, what happens to the answer of that fraction? It increases as well, right? So if F net increases, the net force increases, the acceleration will increase. What kind of relationship is that? That is a direct relationship. So, acceleration is directly related to the net force. If net force goes up, acceleration goes up, right? If we push harder on an object, it will accelerate more. It will change more. If we don't push as hard on an object, it'll accelerate less. It won't change as much. Okay? So acceleration is directly related to net force. So net force directly affects the acceleration. Okay? Good there. Okay? If we go back to our equation, just two ways. If we apply the same force to two different objects, if we increase the mass, what happens to the answer? What happens to the acceleration? If this gets bigger, if the bottom of the fraction gets bigger, what happens to the answer? Smaller. What kind of relationship is that? That's an inverse relationship, right? So, acceleration is directly related to net force, but it's inversely related to the mass. If we push on two objects with the same amount of force, the heavier one accelerates less than the lighter one. Yep, and that's the same, right? Because we're decreasing mass, and that increases acceleration, right? So yeah, that's an inverse relationship too, right? As mass goes down, acceleration goes up, right? So it works both ways. Basically, one gets bigger and the other one gets smaller. Okay? You okay? Say again? Right? As one goes up, the other one goes down, right? So if we make the mass bigger, we get less acceleration out of it. If we make the mass smaller, we get more acceleration out of it, right? So Ronnie, like, for instance, if we take you and you run a race, right, 100-meter dash or whatever, right, you have a certain time. If we put you in like a weighted vest, right, your mass goes up. So what's going to happen to the time that it takes you to finish that race? It's going to get bigger, right? So that means that your acceleration went down because you didn't speed up as much. Does that make sense? Okay? So this shows that inverse relationship. Or if we think about it in terms of, like, you know, if you had, right, a bowling ball and a ping pong ball on the table, and you push both of them with the same force, which one's going to go farther? If you push them, right, with the same force, which one's going to go farther? The lighter one, right? It's going to accelerate more. It's going to end up with a greater velocity, so it will travel farther before it slows down. Okay, I was generalizing. If you push them both at the same, if you measured their velocity right after I pushed them, the ping pong ball would be going faster.
It's gonna go faster, but you said farther.
I did, and I shouldn't.
Bowling ball goes farther because it has more inertia.
But it's not going as fast, so that means that it
It'll
will.
take longer to get there.
If they were going the same speed, the bowling ball would go farther. But if you push both of them with the same force, the bowling ball will never go as fast as the ping pong ball does. So there's a couple different things going on there. Right. So that means with the same force. So that means it doesn't have as much to slow down. It has more inertia, but something that's going 5 meters per second will slow down faster than something that's going 10 meters per second. Does that make sense? There's a lot of different things going on there. So scratch what I said. If you push them with the same force, the ping pong ball will go faster because it has more acceleration.
That makes more sense.
Yeah, the going farther, there's a couple different things we got to worry about there. So. All right, so let's take a look at the application of some of these ideas. Okay, so first let's pull out Concept Development Practice page 4-1. It's got an astronaut on the top of it there. Okay. Now, I realize that if you're looking up on the board, you can tell what the answers are because of the way that this copied and the way I couldn't find the original for this. I had the answer sheet, so I had to delete the answers, you know. So, but still good for us to go through it, right? So, it says, an astronaut in outer space, away from all gravitational and frictional forces, throws a rock. The rock will come to a stop or continue moving in a straight line. Continue moving in a straight line at a constant speed. Once you get a spaceship out of the atmosphere and into space, does it need an engine anymore? Nope. Right? Do we ever, oh, sorry, let's finish this, okay? The rock's tendency to do this is called inertia. Okay? Have we ever talked about Voyager in this class before? The satellite Voyager? Okay, so back in the 1970s, we sent a couple of satellites out to explore Jupiter and explore Saturn. They were called Voyager 1 and Voyager 2. And after they were done doing what they were doing, they just kept on going. And so now, they're still going, right? About, I want to say maybe 6 years ago, Voyager 1 well, no, but if we want to talk, we can talk about that in just a second. Voyager 1 left the solar system. So it's like past the planets, and it just is out there. And it just what?
Wait, can we still get signals?
Yeah, we still, well, we can't see it, no, it's too small, but we still get signals from it, yes.
Like, well,
It sends like radio signals.
I thought the universe was like infinity.
Yeah.
That's the solar system.
So the solar system, like, it went like past Neptune, like past Pluto. I mean, Pluto's still part of the solar system, it's just not a planet. So yeah, so it's like there. But it's just been going for 40 years. And it doesn't have an engine, it just keeps going, because that's what inertia tells it to do. Just go, 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 go. And it will keep going until something makes it stop. Like an asteroid. Right? Like aliens, if we want to go down that road. Right? But,
Get it, they're like,
well, actually, when we sent it, like on the satellite, there is actually a message and like a little map of where we are in the Milky Way, and there's actually a record, because that's how we recorded sounds back when it was like an actual record, and like on that record, there's a bunch of sounds from Earth. There's like a heartbeat and waves crashing and a bunch of different music, and stuff like that, in the hopes that, from the 70s, so, but in the hopes, well, I mean, they didn't just like have 70s music, they had like classical music and like, but they also had things like, I think if I remember correctly, Johnny Be Good by Chuck Berry is on there, like as an example of rock and roll, and, but it's just going.
Where's the Samson?
So people could find us.
Wait, really? Wait, that's the purpose.
That might not be good, but it might be really good. So,
What if an alien guesses it and then they ride back and then they end up on the planet?
I mean, that's a chance we take. Now, consider this, okay? And this is one of those things that, like, when I think about it, it like blows my mind. So, Voyager has been traveling for 40-some years, okay? And generally speaking, when we take things into orbit, into space, they travel about 17,500 miles per hour. Okay, so that's generally speaking how fast our things go. Voyager is actually going a little faster than that because there's a way that you could use gravity to make things go even faster. And we won't get into that right now, but there is. Yeah, like use gravity to like slingshot it, So let's say Voyager is going somewhere in the range of maybe 30,000 miles per hour. Okay. The closest star to us, other than the sun, is about 4 light years away. Well, how far is that? Consider that light travels 186,000 miles every second. So, yeah, warm up, because the other day we did this in my physics class, and it traveling at the speed of 17,500 miles per hour, I think we calculated, and don't totally quote me on this because I can't remember if this is exactly the number or not, but it would take somewhere in the realm of 16,000 years for Voyager to get, 160,000 years, like for Voyager to get to the next star. So, could aliens pick it up? Sure. They would have to go 160,000. Yeah, it has traveled a long way, but in the big picture, it hasn't gotten anywhere. It's like the equivalent. It's like the equivalent of like when you're 5 years old, you rode your bike to the corner. You know what I'm saying? You're like, holy cow! Like I got to the corner, but in the big picture, you really didn't go anywhere. And that's like, generally speaking, what we're talking about here. But the point being that it will just keep doing that because of inertia. It's moving. It'll just keep moving.
Didn't NASA like get to Pluto, say in like a week, seeing as they can get to Mars in 30 minutes?
It takes 9 months to get to Mars.
30 minutes.
It's to send a signal. That's something different. Radio signals travel the same speed as light does.
They said that, I heard that NASA came out like a month ago saying that they had tested and confirmed wormholes and hyperdrive.
I've not heard this.
Proven it.
So,
Just because it happened
Not
in
heard
30
this.
minutes with the Matt Damon movie doesn't mean it happened in 30
So-
minutes in life.
so I have not heard. I have not
That's from
heard
the
that.
future. That movie takes place like.
Yeah, and the idea of traveling through a wormhole is there's a whole bunch of technological issues that we probably have to consider there. You know, like
Seeing as NASA had technology in 2001 that they only came out with in like 2015,
being able to do
we
something.
only thought that we would have 2030. What do they have now?
Being able to do something and then having the money to do it reliably are two different things. Just so, like, let's get that clear. Like, not sure. So.
Just listen to it on this.
All right, yeah, you can watch the video. You can watch the video of this. All right, so in another example, the next question on the sheet there about concept 4.1 or 4-1. So you take this rock, tie it to a string, swing it in a circle. We've discussed that as this rock is moving in a circle, it is constantly accelerating, right? Because what keeps happening? It changes direction, right? But that happens because the string is attached to it, and the string is applying a force. Any acceleration requires a force. If the string breaks, is there any force acting on that rock anymore? No. So what does it do? Just keeps going in whatever direction it was going. So when it gets to the top of the circle, at that instant, its instantaneous velocity is in that direction. So if the string breaks, it just keeps going in that direction. Okay? Does that make sense? What? Yeah. So if you look at this, right, you're actually looking at this from the top. So it's like I'm swinging it like this, but you're looking at it from the top. Okay? Because if I break the string right now, right? Well, it'll go straight, but it'll also go which way? Down because of what? Because of gravity. Well, in this pit, right? If you're looking at it from the top, you really can't see gravity. You know what I'm saying? Yes, Jafar. So I can do this. So I can do this demonstration. So, you know, so this was an electrical cord from an old lamp at my house, and this baseball is not a good baseball. It doesn't have the cushion cork center. It has like just a plastic center. It's like one little kids use like for t-ball and stuff like that, you know. So I just drilled a hole through it so I can do this demonstration. So. Yeah. Oh, I do this demonstration. I do this demonstration like 7 times a year because what? Not very. I mean, like it's just plastic in the middle. Like it's not. Yeah. So not very long. All right. Taking into account that idea of gravity, let's take a look at number 3. So it says, suppose you're standing in the aisle of a bus that travels along a straight road at 100 kilometers per hour. That's only like 60 miles per hour. You hold a pencil still above your head. So if you don't like a pencil, you can call it whatever you want to. You have something in your hand as you are standing on the bus. Then, relative to the bus, the velocity of the pencil is 0. Because the pencil and the bus and you are all traveling at the same speed. Does that make sense? Okay there? But even though it appears to you that the pencil is standing still, in relation to the road, it's traveling 100 kilometers per hour. Or relative to some guy standing outside of the bus on the sidewalk or something like that. Okay? All right. Here's where inertia takes over. All right? Suppose you release the pencil. While it's dropping, relative to the road, the pencil is still traveling how fast? It's still traveling 100 kilometers per hour. Now, we discussed that gravity causes acceleration, right? Things that are falling will speed up. But gravity only affects things which way? Downward. So this pencil will speed up while it's traveling downward, but is there anything to stop its horizontal motion? No. So inertia tells it to do what? At least horizontally. Keep going. Right? And that means that if you drop the pencil while the bus is driving, where is it going to land? Well, in your hand or by your feet. Right? Because what are you also doing? Well,
relative to the road.
Relative to the road, you're going 100, right? And so you keep going forward, the pencil keeps going forward, the bus keeps going forward, right? And even though the pencil is falling downward, everybody else is just keep going forward. It looks exactly the same. Would it look any different if you were standing still, if the bus was stopped?
No. It's the same.
It would be exactly the same. Okay? It's like this demonstration here. Okay? Alright, so I've done this demonstration a ton of times for you, right? Ready? Ball goes up, comes back down, lands in my hand. Alright?
Sorry, can you do it again?
Alright. Yes, Mike. Let's talk about it. Here, I'll do this demonstration for you right here. Okay? Ready? So, standing still. Straight up, back in my hand.
You do the same thing if you're on a bus going.
Okay? As I'm walking forward, now the ball is moving forward with me. Right? Okay? So the ball, its inertia is telling it to keep going forward. I throw it, but I throw it upward. The ball was moving which way before I threw it? Sideways, forward. Is there anything to stop it from moving forward? It'll go up and come back down because gravity is affecting it vertically. But what does it do horizontally? Keeps going. Inertia. Right? So, it lands in my hand if I just throw it up like this when I'm standing still. It lands in my hand if I'm walking forward. If I was in a car going 35 miles per hour out on the road, right? Could I do this demonstration while I'm sitting in the car? Yes. If I was in a, well, yeah, if I didn't hit the ceiling, right? Would it work if I was on an airplane going 500 miles per hour?
Yeah.
Yeah. As long as what doesn't happen to me or the ball. As long as I don't what? Speed up or slow down. Right? This experiment doesn't work if I do this. Ready? Here we go. Walk, walk, walk. Throw.
Because that's going faster. The inertia has it going.
The ball's inertia
Momentum.
kept it. No, let's not use that word. That's something different.
Momentum.
Okay? Don't use that word. It's something different. Right? The ball's inertia keeps it going forward even after this is going up and down, or even while this is going up or down. But what did I do? I stopped. So it didn't get in my hand, not because inertia didn't work. Inertia did work. I just stopped. Good.
So inertia is like you're sitting at the bottom of the going like 100 miles per hour and then you stop and then it's like crash.
Yep. That's why you need seatbelts or airbags, right? Because if you're in a car going 100 kilometers per hour, you're going 100 kilometers per hour.
Isn't the ball
Oh yeah.
so like you're
Well,
going at speed but you're strapped in and
right.
the ball going up?
Yeah. Like, or, I mean, have you ever been in a car before where somebody slams on the brakes and, like, you know, if you have, like, books or something in the seat next to you, right, that all goes forward because there's nothing to keep it from going forward, right? Same thing with you and a seatbelt, right? That seatbelt applies a force to you and causes you to slow down. But if there's no seatbelt to slow you down, you just keep going. Okay? Yes, Ron.
Yeah, I thought it was
Hey,
cute.
hey. Ronnie, good.
Okay, I'm on the second gear. The doors are running in your car and there's Mercury on. And you're running the same speed as the car. The car goes really slow. Yeah.
But if you're just standing still,
When you crash, what would happen?
You.
This says I need to do
Okay.
this.
So I got it. So you're running. So let's say, all right, let's say you can run 10 meters per second, okay, which is pretty fast, but that's not out of the realm of human possibility. Okay? 10 meters per second, and the bus is going, let's say, 40 meters per second, which is pretty fast, but that's okay. That means relative to the road, you're actually going 50 meters per second. Does that make sense? Okay? So, because you're already going 40 from the bus, plus then you add another 10 from you running, that gets us up to 50.
so then
You would still crash, yeah. Actually, you would actually hit the windshield or the front of the bus faster than somebody who was just sitting on the bus. Does that make sense? Because they're only going 40, right? And you're going 50, right? And it's also why, like, you know, that's also why, like, on the school bus driver's not supposed to drive with you standing up, you know, like, or when you're on like a coach bus, you know, there's like that little yellow line, like a nice bus, like one you took to DC or something like that, you know. What?
Yeah, there's yellow lights. Who would drive those drivers?
Yeah, like up in the front, like right at the, like there's like a yellow line, and the driver's like, hey, if you're standing there, you're like, I can't drive while you're past that yellow line because of inertia, right? When you're on the bus, if the bus stops, the bus feels a force, so it slows down, but you don't. You just keep going. All right?
So, say you're on a plane,
Yeah.
and you just had like a perfect like place of the train's going 500 kilometers an hour,
Yeah.
and you run.
Okay.
Since you already have the speed of the plane,
Yeah.
you run as fast as it is. I don't get that.
Isn't it even running faster?
Yeah, you're running faster than the plane. Like,
Oh, that's true.
yeah, because you have 500 from the plane. I mean, that's true even if, like, when you walk from the bathroom in the back of the plane to back to your seat, you're traveling faster than the plane.
That is true.
Like,
Oh, I'm faster than the plane.
you are faster than the plane.
So then 500 miles per hour would be
I mean, you can't do it on your own. You need help from the plane. But yeah, but I mean, but technically though, so going back, this is actually a picture that I drew in the previous class. Okay. So if this is a rocket ship, and the people are in the rocket ship, you're going as fast as the rocket ship. So in this case, everybody's going 17,500 miles per hour. And you can't walk because, like, one of the reasons why people float in space, not because it's floating, and not because there isn't gravity, because, look, so,
Oh, this.
okay, so if I drop both of these, right, what happens to them? They both what?
All at the same time.
They both accelerate. They both accelerate at the same rate, so they hit the ground at the same time. Okay? Now let's say, for instance, okay, if I let this go, but this room wasn't like on the ground, okay? It was like suspended in the air. And then I let the ball go at the same time the room was like cut from the suspension, right? The ball starts falling, the room starts falling.
It's like it's floating.
They're both accelerating downward, but is the ball getting any closer to the floor? Because the floor is going at the same rate. So the reason why astronauts float in space,
It's because they're not so speeded.
they're falling just like the spaceship is falling, and so they don't get any closer to the floor of the spaceship. And so that actually, we can recreate this situation here on Earth. This is actually how we train astronauts, but also we film certain scenes of movies that are in space. There's a big plane, and it's called they call it the vomit comet, because when you see what happens, this is what happens. Okay. So here, so there's plane, okay, and let's see if I can do this. Okay, so there's the plane, okay,
Don't pack up.
okay. So the plane goes up. No, come on, come on. Okay, so they fly the plane. God, I'm trying. Like it gave me like this little cross right here, you know? Like, see the cursor? All right, there we go. Okay. All right, so they fly the plane up like this, okay? And then when they get to the top, they get, I don't know, 35,000 feet or whatever, okay? Come on, now it won't even give it to me, okay? Then, so then they do this.
Oh, that's bad.
And all the people inside, right?
Just start floating.
Yep. Right? So they just keep doing this over and over again, and depending on how high you well, inside of the plane, you are weightless. For the same reason that astronauts are weightless, because you're falling and the plane is falling, but you guys are falling at the same rate, so you don't get like any closer to the front of the plane. Does that make sense? Right? You can actually, there's a company out there, we've looked it up in class, it's called Zero G. You can do this, like you can pay and
They like turn off like almost all the don't they like vacuum out so that's
not in that plane, no. Like that would be more of an astronaut training thing. But like the inside of the plane has like some seats for when you take off, but the inside of the plane is it's got like all padding on the floors and the walls, and like I think it's like $5,000, but you can take it's like a 3-hour flight and you just like go up and down. I think it's like 12 times or something like that. And you can experience what weightlessness is like. That'd be pretty awesome.
Which water planes do you? That's what